Let's start our second lecture. And our second speaker is Mr. Jonathan Dyson. He is going to speak on selecting reinforced concrete CP system. And it's my pleasure to say a few words about Jonathan. Mr. Jonathan Dyson is a durability engineer and the New South Wales manager at BCRC. Jonathan has 10 years experience in the design, construction, maintenance and repair of concrete structures. Before joining BCRC in 2013, Jonathan's diverse experiences early in his career included roles in consulting, structural engineering, construction management, and design management. Jonathan is a chartered professional engineer and a member of the Civil and Structural College of Engineers Australia. He is also an associate of the Institute of Structural Engineers UK and a committee member of the New South Wales branch of the Concrete Institute of Australia, as well as being a member of Australasian Corrosion Association SEA. Jonathan, it's for you.
Today I'm going to be presenting on a paper on selecting reinforced concrete cathodic protection systems. Firstly, I'd like to acknowledge my co-authors, Mr. Frank Popeworth and Mr. Mark Magaziki, for their valued contributions. So the paper focuses on cathodic protection for concrete in atmospheric exposure. Firstly, I'd just like to touch a bit on the status of CP concrete structures in Australia. The first reinforced concrete cathodic protection system was installed in Australia about 30 years ago. It was a conductive paint. It exceeded the 20-year design life, so that was good. Designers, contractors, owners on small to medium repair projects still, though, they often are ill-informed about the benefits of CP. Some of these benefits compared to alternatives can include cost, occupier friendliness, structural outcomes, and repair reliability. I'll go into more detail further in the slides. The confusion between the various types of systems, there is confusion between the various types of systems that are available. They generally fall into one of three categories: cathodic protection, corrosion control, or cathodic prevention. Cathodic protection is when you have a high polarization of the steel that achieves the requirements set down in codes. Corrosion control is not all that well defined, but it's generally somewhere between cathodic protection and cathodic prevention, and it reduces the corrosion rate of active steel, but does not provide cathodic protection, full cathodic protection. Cathodic prevention is when you low polarize the steel to protect unfitted rebars, and you increase the chloride level that is required to initiate corrosion. There'll be more detail on this in the later slides. CP codes that are available today generally provide little guidance on how to select an appropriate anode system or complete a risk assessment. And therefore, robust selection is a process that is rarely undertaken, unfortunately. Technology confusion often leads to misdirection, and designers are often not expert in CP, and they therefore prefer to specify what they're more familiar with concrete repair, and that is patch repair systems. So the objective of today's presentation and the paper is to show that there would definitely be additional benefits from additional guidance in this area, and that would be of benefit when choosing and specifying cathodic protection systems. The first step one should always undertake is to gain a really good understanding of the extent of the problem by testing. So you can have a situation where you have widespread repairs, such as a jetty over here that's above seawater. You've got relatively uniform cover, and you can go from having around 20% of the soffit drumming and spalling to around 80% of the soffit spalling and delaminated within the space of 2 years. So initial cracks can warn that there may be a widespread issue, and at this stage parcel potential scans should be done, not just a visual assessment, to fully understand the extent of the problem. CP, cathodic protection, would be a suitable protection measure when there is, say, 20% spalling. However, if you're at the stage where there's 80% spalling in this instance, CP is probably not going to be as practical and as feasible as simply replacing the whole structure. The other side of the coin you could have is a situation where you're only really having to deal with localised repairs. You might have a few spalls that say 20 plus years of age. You've got localised low cover, but not extensive. You might have relatively low carbonation or chloride ingress. In this instance, you're probably talking about a patch repair system being the best option. You might have a few more spalls over the next 20 years, but generally you won't have many more major issues for the next 40 to 50, until 40 to 50 years later. So additional testing is undertaken to establish the cause and extent of the deterioration and the future prognosis when they're not apparent from visual assessment. There is a standard process that should be undertaken for use in investigations. One or more initial non-destructive scanning methods should be used to divide the structure into zones of different condition. Then more detailed measurements specific to the condition state and the objective sought should be undertaken. It's not appropriate, for example, to launch into a coring program which is extensive and destructive without having some idea of where to core first. Taking pot luck on where to take strength cores may lead to sampling only an area of good concrete or an area of bad concrete. And so a principal reason for doing the first testing is to identify where to do follow-up tests. Reinforcement potentials will show that areas of active corrosion and areas that are still passive, so the chloride profiles and samples from passive areas can be used to give residual life. The same samples taken from an active area will only tell you what the lower cost and much broader applied potentials has already told you, and that is that the steel is active in that area. Rebound hammer tests will give an indication of strength and quality variation so that the limited number of cores can be taken from areas of both high and low strengths, and rebound values can then be calibrated against those. Cover scanning with the GPR can give a very quick assessment of cover in order to pinpoint areas where low cover is the cause of apparent distress, and to give a cover distribution which can be used in conjunction with the chloride activation front or carbonation front depths to then give you the residual life. However, care does need to be taken when interpreting data from non-destructive testing, and that should only be done by experienced and knowledgeable practitioners. For example, two recent projects we've been involved with had oxygen-starved rebar, and before we got involved, low potentials had been used as a base for specifying widespread photo protection. One of these jobs had a $2 million photo protection system design, which was actually, it turned out not necessary because the low potentials were a result of the oxygen starvation rather than the steel actually being active. Some other examples include rebound hammer results being used on carbonated concrete, giving higher strength due to the carbonation that is actually the strength of the in-situ concrete. And cover at lapse, showing that lower cover on the cover meter readings than you will actually have in the structure. So these things need to be carefully considered. So the next question is, how much concrete do I break out? Whatever the repair method is chosen, all fractured concrete needs to be removed as a first step, unless that is it's decided not to repair at all and simply to fence off underneath the spalled areas to make it safe. This is obviously a cheap option, and it can be a suitable option in some applications. However, assuming that repair is a preferred option, a decision on the breakout extent is required. One option could be just remove the fractured concrete and simply patch those areas. This would be a cheap option, but will always only give you a short life. Another option, a more extensive breakout behind and along the bars to remove the contaminated concrete. This can be very expensive and destructive, and can also compromise structural load paths. On the repair of a heavily reinforced support structure, the contractor made a large claim for breakout around the base of columns in the photo on the slide. This was because starter bars were not shown on the drawings provided, and access between the bars to break out the strong concrete was very limited. If concrete surrounding more than 50% of the bar is removed, there is a good chance that the bond may be broken, such that simple patching does not fully restore the bond strength. Where this is critical, for example in anchorage zones, it may be needed to clearly break out around the full bar in order to achieve that bond. Breakout can be very damaging and cause effects that are hard to overcome. Breakout can leave small reinforced core in columns, for example. This core can remain over overstressed after patching unless stress in the core is relieved, preferably before the breakout. And this can become a very expensive process. So, as an alternative, an option to remove only the fractured concrete and apply cathodic protection can be attractive. This can provide low patch costs and lower disruption, and it can also limit the overstress of the structure. There's been some debate about whether the incipient anode effect in a patch repair was a real or purely theoretical concept. This slide shows a schematic of samples made by Barcade. He was able to measure quite precisely the corrosion because his bar was made up as a number of separate sections so that he could measure the current flow. He's also developed a theoretical model that matched the experimental data. The results showed that corrosion rate is controlled by the resistance between the anode and the cathode, and hence potential difference is not a key control mechanism. The incipient anode area was quite small, only 5 to 10 centimetres long, and it was quite close to the patch, 1 to 2 centimetres away. This was significant because it confirmed that sacrificial anodes within the patch are able to control the whole incipient anode, and that the majority of current was towards the repair. Again, this was significant as it shows that the epoxy coatings on the rebar in the patch area, which is typically what happens, will largely restrict the cathodic area and hence the corrosion rate of the incipient anode. This graph shows the zones of passivity based on chloride content of the concrete and the electrical potential of the reinforcement. After an element is constructed, we start at number 8. We have no chlorides and passive reinforcement potentials. As the chlorides at the steel increase, the reinforcement moves to the area where pitting occurs, and we get corrosion damage. The electrical potential will decrease relative to the areas of steel passive rear. If, however, we polarise the passive reinforcement just a little at the start, before we have chlorides, we then can have a much higher chloride content before we reach the area where we will get pitting. And so a small shift in this way provides cathodic prevention. If we polarise the pitted reinforcement just a little from D to E, corrosion would continue, albeit at a slower rate, as the pits continue to corrode in the zone of imperfect passivity. If, however, we polarise that reinforcement a lot, we take it to the perfect passivity zone and corrosion stops and we have achieved cathodic protection. The small potential shift of passive steel is called cathodic prevention and is being applied to new structures in Europe, particularly Italy. It could be simply installed to many structures in severe exposures to reduce the cost associated with high cover and to reduce the risk of premature failure. For concrete repair for incipient anode protection, where prior to the repair the halo around the anodic region of the steel was protected by the anode and hence had no pitting, use of lower powered sacrificial anodes can replace the reinforcement that acted as the anode prior to the repair. The small potential shift cannot provide protection to reinforcement that has already started to corrode, which is why it remains important to achieve fully effective patch repairs in these circumstances. A large potential shift in corroded reinforcement is cathodic protection. This can be used to prevent the need for breakout of concrete around corroding bars and give major reduction in breakout costs, as previously explained here. Talk a little bit about sacrificial anode cathodic protection now. This graph shows that the corrosion rate of zinc versus the pH of the electrolyte. When we place zinc in concrete with a pH of around 12, it passivates. An oxide layer forms, prevents it from corroding and giving protection to the reinforcement. So very quickly it will stop working if we don't do something to keep it active. The anodes that have been commonly used in Australia use a zinc puck in a lithium hydroxide porous mortar. This puts the zinc anode in a high pH environment so that it will corrode and provide a level of protection to the steel rio. The reaction products that form are zinc hydroxides. These are expansive, but the porous mortar is designed to enable that expansion without failure stresses occurring. Other zinc anodes use a slightly acid gel that contains chlorides to keep the zinc active. The reaction products are zinc chloride, and these are non-expansive. They are soluble, so they move into the gel and don't block current supply. They're also hygroscopic, so they draw in moisture and help keep the resistance of the anode low. High output and low output sacrificial anodes have different properties. The top group of sacrificial anodes are designed for cathodic protection and have a high current output. They are all the same family based on zinc sheet with a pH 5 chloride based gel. The positive attribute is that the electric The electrical cell produced draws chlorides from the bar to the zinc. This fuels the protection and ultimately leads to passivation of the rebar. These anodes give a high current output, which means a high zinc mass is required to give a moderate life at moderate reinforcement levels. An advantage is they only need loose concrete to be removed, so the anode is paid for by the elimination of hard breakout. However, they are not economic as a direct replacement for low-powered anodes because the high output and hence high consumption rate means that sensors will need to be closely spaced to give a reasonable life. Three types of anodes are typically available. The sheet is applied to the concrete surface and then coated with a waterproof membrane. The cylinders are placed in drill holes and the pucks are embedded in a patch repair. The lower group of anodes are designed for cathodic prevention typically and have a low current output. Common anodes are zinc in a lithium hydroxide porous mortar. The low current output means a slow loss of zinc. The anodes are generally embedded around the edge of a repair to protect only the incipient anode. The reinforcement in the patch is normally coated with zinc-rich epoxy, reducing the area of the cathode and further slowing consumption of the anode. There is a need for a method to assess sacrificial anode output, and then there's a need for a method of SACP design based on the anode output, the resistivity and the reinforcement layout. Currently, there's a bit of a lack of guidance in the codes in this area. One option could be the application of cyclic voltammetric tests, similar to what's shown over here. This is a standard test used in electrochemistry and is similar in concept to anodic and cathodic polarization curves. The system is set so that the voltage is cycled and the current measured for a given anode. Where the anode and cathode curves cross gives you the system potential and the current. These tests, done by Giordini, show that the zinc and pH 5 chloride-based gel gave a very high polarization, but also high currents and hence high zinc consumption rates when the zinc and lithium hydroxide gave low polarizations. John Broomfield in the UK is currently working on an ACE standard to measure the performance of galvanic anodes. Such a standard will be of great benefit. Early age test results are commonly offered as proof that a galvanic anode system is effective. However, this is no proof that the anode will work in the long term. On an overseas project, the zinc layer anode was installed in 2003 to the outside balcony parapets. 24 hours, monitoring was maintained for 6 years. 8-hour rather than 24-hour potential decay measurements were convenient as they could be undertaken on one visit to site. 6 years after installation, decays were well over the code's 24-hour decay requirement of 100 millivolts. So you've got your criteria as the line, and you've got your 8-hour decay. It's achieved much more than 100, as can be seen. So in fact, the performance in terms of code criteria is improving as time goes on. This is expected due to the realkalization effect around the bar. Sacrificial anode systems can't be turned up, turned down, or inadvertently turned off like compressed current systems. Because of this, monitoring and ongoing adjustments are not really relevant. The cost of monitoring is expensive because it means a wiring system so that all the anode connections can be turned off to measure the potential, and embedded half cells will need to be installed with cabling back to a control box. For a small balcony, the cost of installation would be doubled by the monitoring. Hence, on small systems, galvanic anodes are generally installed with no monitoring. These small systems can be designed so that for no or very small additional cost, they have a very low risk that the system won't meet the 100 millivolt potential decay criterion. On larger systems, say 100 balconies, a couple of the balconies could perhaps be monitored for a small increase in overall project cost. These examples on the screen, I'll just quickly go through just some Australian sacrificial anode installations, a beachside apartment balconies offered in Western Australia where zinc sheet was applied. Low cost, easily installed, provide global protection, and after 20 years was replaced with a coating. An undercroft garage in Victoria where there was soft carbonation was protected, and some discrete sacrificial anodes in a bridge in New South Wales where sacrificial anodes were used because there was an inadequate budget for ICCP for all structures that needed to be cathodically protected. Moving on to compressed current CP. Generally this has long life and is fully monitored. Typically it uses mixed metal oxide titanium anodes, and the current is adjustable, and it's important not to overprotect and lead to hydrogen enrichment of particularly pre-stressed structures. Costs relative to sacrificial anode, well, the design costs can be okay for large repetitious structures. Anode costs can be moderate. Anode embedment costs can be high. Wiring and control costs can be high, particularly for small projects. Maintenance costs can also be high. Reliability is the key criterion, and it's important that current dumping risk is considered and mitigated. And specification should be by performance rather than specifying the use of a particular supplier. Broader testing requirements need to be developed, and the pictures show some of the types of quality testing that can be done to ensure the quality of, in particular, the thin mixed metal oxide coating is acceptable and will provide the reliability required. Some of the typical titanium mixed metal oxide anodes. Mixed metal oxide ribbons and nets have a titanium base with a very thin annealed multi-layer coating of stabilised noble metals, oxides. The process of how these work is not important here. All we really need to know is that the MMO coating has an extremely low consumption under current flow, and hence, even though thin, has a long life. Quality assurance of the MMO is critical, as previously mentioned. There are several manufacturers that have been, and there have been some serious failures of overseas supplied products, so it's very important to prove the quality. And quality assessment is usually based on weight loss testing to NACE standards with clear acceptance criteria, and also based on experience of use in the field. There are several MMO titanium anode types commonly used. As mentioned, the mesh and the ribbon. I'm just going to briefly talk about these because I've got to move on. So there's the mesh, which is typically a bit like chicken wire, can be rolled out and pinned on the concrete surface. There are ribbon mesh, which can be embedded in slots in the concrete. There's solid ribbons. There's also some discrete anodes types, which you embed into the concrete rather than apply to the surface. These can have benefits, including providing local or distributed protection. They can be used in conjunction with other systems to target otherwise missed areas. They can provide protection to deeper into the concrete, i.e. opposite face of a wall, where only one face is available, or another example could be, all faces of a column from accessing only one face. I think I'll move on to the next slide. Some surface-mounted types of anodes. In many cases, embedded anodes are not the optimum solution, so manufacturers have developed a number of proprietary systems that may be more practical. For example, there's a cassette system, which is, instead of cutting slots in the concrete, got an MMO ribbon mounted under a pad inside a fiberglass tray, which is then bolted to the concrete surface. You've also got, on building facades, it can be difficult due to the thin elements and weight limitations, so conductive coatings were developed in the 80s and have been used successfully on buildings and bridges. Another option is precast discs that contain a fine MMO mesh in an acid-resistant mortar. These can be run at relatively high densities, and they can also be used as an architectural feature, believe it or not. Sometimes that is actually occurring. So how do you select an anode system? There are codes that say that they provide CP installation testing and performance requirements, and they give background on information of different CP systems. But they don't provide a lot of systemic guidance on selecting an anode system. So at BCRC, we've developed a system for evaluating CP systems based on 2 acceptance themes, each with multiple factors to consider, applied on an element-by-element basis. Theme 1 is the suitability for the client. So we review CP systems. There's a 5-point scale is used to assess each suitability factor and a weighting applied to that is specific to the project and the client's needs. The second theme is cost, where we provide an indicative pricing, and we look at both initial and maintenance costs, and we only look at the systems that have already met the client's needs or haven't been ruled out from looking at the suitability factors first. Systems that are both economic and meet the client's needs are incorporated into a CP specification so that they can be priced by the market. An example of this system being applied, 5 minutes is it? Yeah, thanks, is for a basement ICCP project where the suitability factors were assessed first, and anodes not meeting the owner's preference were discarded. Remaining systems were then assessed on both themes. So one of the suitability factors assessed was reliability, another was install speed. Owner's preference was to have work done completed quickly, as will always be the case. However, this had a lower weighting compared to reliability. Customer friendliness, so noise and dust were the considerations there. Flexibility and aesthetics. Some systems obviously have a higher aesthetic rating than others. So the cost factors can be tempting for owners to focus predominantly on initial cost when available budgets are limited, but maintenance costs should always also be considered, and we always do that in the PCRC approach to have a look at whole of life costs. However, the weightings between each can be tweaked depending on the owner's requirements. So the aim of this CP system comparison method is not to enable a final CP system based solely on the weight and cost and suitability scores, but rather to act as an informative guide to assist owners and stakeholders in making a decision. Where anode systems are shown to be positive or negative on the cost or accepted score, the reason behind that score should be reviewed to ensure the scores give a reasonable impression of the anode acceptance. Another example is an old building in Sydney where there was a call for bids based on no condition testing at all, and the bids were only specifying use of a hybrid system. Tenders then identified alternative systems and issues with the limited availability of hybrid designs. The owner then requested an application of the BCRC approach, which identified that two sacrificial anode and two compressed current systems were possibly better suited than the hybrid system initially specified. It also showed that there was a need for statistically based testing to fully understand the structure's condition and to